So what kinds of ideas do y'all have? Like, given what you've seen here, given the hints, given the equation, anybody have a thought? Sydney, did you raise your hand? Okay, so we have some guesses / votes, right? So Adam, earlier I heard Adam say 40. At least some subset of that group thought 60. Anybody come up with anything else? Yeah?
55.
55. I know somebody who, well, yeah. Who are you going to award that F to is what I want to know. Yeah?
I changed my guess to 42.
42. All right. Kai? 54. What is it? You're just guessing. These are just, this is like name that. What's the Price is Right?
35.
35? Oh, he's going out on a limb. So here, I'm going to time out here, because what I want to know is not what your guess is, but how did you get it? Where did you get these numbers? How did you do it? Yeah.
I did like what looks like the average version of 6.
Okay.
Maximize,
Okay. So we have one vote for eyeball the average force. And that makes a lot of sense. The problem with that approach is, what if the graph looks a little bit different? What if the graph looked more like this? That's ridiculous. Okay, but you get the idea. So, you get the idea. Like, this is a little bit more difficult to figure out the average force for. Or even if it was some sort of a regular shape, what if it looked more like this? Where, like, this almost looks as if like we can sort of eyeball the middle, but this isn't going to be the middle. That's not going to work. The middle number, right, half of the maximum, is not going to give us the information that we need. So, what's another way we could do this? Do you remember when we were looking at velocity versus time graphs, and we recognized that average velocity times time would tell us displacement? We figured out that displacement is equal to average velocity times the amount of time that goes by. Look at the similarity there. What did we do with the velocity versus time graph? Does anybody remember the trick we used? Yeah?
Find the area under the
We made shapes, yeah. And the shapes, we weren't using geometrical area. We didn't care how long or how wide these things were in inches or centimeters or feet or yards. We used our axes as our measurements. So for example, we can kind of think of this as being like a triangle to there, and a triangle to here, and like a sort of weirdish rectangle there, and a triangle here. And how perfect is that? Really not perfect at all. But I bet it's actually pretty close. This triangle here is 3 by 3, so this one would be about 4.5. This triangle is like 1 by 3, so this triangle is about 1.5. This rectangle is 4 by 3 or so this would be 12. This triangle goes from about 3 to 12, so it's 9 tall, and it's 4 wide, so that's 36 divided by 2, it's about 18. What do we get? That's 30, 35, 36. Who is our 35? Wyatt. Who's getting the F?
Nick. What?
Sorry, man.
That's a tough luck. Better luck next time.
Let's make him stay in the class, though. I think that's fun. All right, so this kind of a methodology would actually work really well if you had an accurately made graph and you were able to scale things so that you could accurately find the area. That would work. If you didn't have an accurately made graph, but you knew roughly the equation for the amount of force as a function of time. Like if you had some mathematical equation that like force equals something times, you know, we could do it with calculus. Because if you're in calculus or far enough in pre-calculus, you've heard about this mythical area under the curve. That's the integral. So whatever equation draws that curve, if we integrate that equation between 1 and 11 seconds, that will tell us the product of all that force by all that time. But that's kind of impractical in a lot of ways. So we have another way that we can look at this, and this is how we're going to look at it, and that's to use the average force. And I'm not going to have you do this because we have a short class period today, but what I want you to think about is like, so why is it that this and average force are essentially the same? And there's two ways to think about it. One way is to kind of think about, well, if we take this and we kind of chunk it up and we took those chunks and we put them here and filled it up, then eventually what we get is a rectangle. And that rectangle would represent a constant force over a period of time. In this case, if our well, you know, roughly 11 seconds, our average force looks like maybe it's about 3, if my calculation is reasonably close to correct, which it's probably not. So we can sort of eyeball it. There's another way to think about it that I just want to throw out to you, and this is not something that you're going to need to have, like, you're not going to need to apply this necessarily to this particular graph and this particular curve, but those of you in AP Physics are almost certainly going to need to provide an explanation for something that is along these same lines. So if we think about this curve in terms of like being composed of rectangles, we can think like of even width, of even amounts of time. And what we can do is we can draw the rectangle so that if this is our curve, we'll draw our rectangles so that the midpoint of the rectangle is at the average force for that whole section. So I'm not going to be able to draw it super well because I can't draw it super well, but it would end up looking something like this, right? We have these rectangles, and every rectangle is the same width, and they all have their left-hand side outside of the curve and their right-hand side in the curve, and halfway in between is the average force for that area. So it's going to look like this the whole way, and I really can't draw, so I apologize, but this is effectively what we're looking at here. And what you can see when you do this is that each one of these rectangles is going to have an area equal to the average force in that section times the amount of time that goes by. So every one of these rectangles is average force divided or multiplied by time. And if we want to find the overall average height of all of these rectangles, we could do that as well. We'd add up all these average forces and divide by the number of slices that we got. So if this is an average force times a relatively short amount of time, and this is a different average force times a different amount of time, we could find the area of both of these combined by finding the average of these two average forces. And that's effectively what we do in calculus. In calculus, what we do is we take a curved shape like this and we divide it into an infinite number of infinitely thin rectangles. And then we find the area of each of those rectangles and add them up. Each rectangle is a line. It has an area of 0, except it doesn't, because when you add up all those lines, you get the area of the full shape. So mathematically, this is a lot easier to do with calculus. Even finding the average, in this case, is really tricky, because how do you find the average of a smooth curve like this? And the answer actually is that we personally wouldn't do that. That's not something that I would ask you to do mathematically, but our computers can. If you have a curve that looks like this, say in graphical analysis, if you highlight this section of the curve and then choose the statistics button, which is the button that just kind of looks like this, it's a curve, it will tell you both the average force and the amount of time that goes by, which means that when you set up your collisions using the super cards and you use the force sensor in one of the cards, you have a super easy way of finding average force and the amount of time over which that average force was exerted. It also can do the calculus for you and tell you the area under the curve. If you select the right area, both of those numbers should be really similar. Worth maybe playing around with if you're in calculus. If you're not in calculus, it's probably not worth it. So what I would like to have you all do today is go back. Oh, that's not one. Go back to what we were looking at the end of the period on Thursday, which was coming up with an investigation. And I'm gonna give you all a little bit more direction here. So bear with me, because what I want to do is kind of lay out a way of thinking about this that's going to provide us with a guiding question and an associated hypothesis that we can use. Okay, so stand by. My keyboard stopped working. All right. So here's how we're going to think about this. We're going to think about each individual card as being its own system. Pretend that it's completely standalone. All right. So if we have this cart over here, we have this cart over here. Holy cow! And we'll just call this. Well, that's yellow. So let's call that cart Y. And then we have this cart over here. That's cart G. And what I'm going to do is I'm going to engineer a collision where they're moving toward each other. And then what happens after they bounce off each other, I'm just going to observe it. Moving toward each other. Afterward, my yellow cart kind of keeps moving and my green cart switches direction. So I have a before here, which is my yellow cart is moving this way, my green cart is moving this way. And then I have an after, which is that my yellow cart is still moving this way, just more slowly. And my green cart, after the collision, is moving completely in the opposite direction. And here's what we know about both of these carts. We know from the work that I did in the derivation of Newton's second law, conservation of momentum, and impulse. We know that the impulse acting on this cart will be equal to its change in momentum. And remember, I told you, they're not the same thing. They're mathematically equivalent. Impulse is a force acting on something over some amount of time. Change in momentum is the difference in its momentum at some later time from some earlier time. But those two things will be equal to each other. And that followed from Newton's second law and our definitions of acceleration and momentum and impulse. So what does that mean? Well, we measure impulse by looking at a force. So the average force acting on our cart 1 times the amount of time that force is acting, that's the impulse acting on cart 1. That should be equal to cart 1's change in momentum. That's its mass times its final velocity minus its mass times its initial velocity, right? So we know that's true for cart 1. And we know that the same thing is gonna be true for cart 2. These are two completely different systems. Cart 2 is also experiencing impulse. The impulse cart 2 experiences will equal its change in momentum. So the overall average force acting on cart 2 times the amount of time over which that force is exerted will tell us the difference in cart 2's final velocity times its mass minus its initial velocity times its mass. Okay, so this has to be true. We know this. If we were to make measurements, if we were to look at cart 1, measure the average force, measure the amount of time that average force occurred over, look at its change in momentum by measuring the difference in its final and initial velocity and looking at its mass, if we were to do all that, what we would see is these two numbers are pretty close to equal. If we did the same thing for cart 2, for the green cart, we'd see these two numbers are pretty close to equal. But here's what's interesting. These can be considered separate systems, but we know that they interact with each other. There's only one collision. This collision right here is equal to this collision right here, not, I mean, in just a general sense, right? Like it's the same collision. Both carts are experiencing the same collision, the same time. So that means it seems reasonable that there might be some connection between what's going on with cart 1 and what's going on with cart 2 in terms of its momentum, change in momentum, and impulse. We know this is true. We know this is true. It kind of makes sense to think, just intuitively, that maybe the impulse acting on cart 1 is going to be the same as the change in momentum cart 2. Why? Well, there's something symmetrical going on here, right? Like there's the same collision and these two carts are hitting each other and whatever is going on with one is kind of going on with the other, and I don't know that I can put it into words, descriptive words, but the idea of this as a testable hypothesis holds some appeal. Is possibly the impulse acting on one of these carts going to be the same as the change in momentum of the other cart? So here's how we can investigate this. We can, first of all, kind of restate that and frame it as a question with words. And that question would be, what is the relationship between the impulse acting on one cart and the change in momentum of another cart. And so in order to figure this out, we have to be able to calculate impulse on one cart. We have to be able to calculate change in momentum for another cart. That means we got to make some measurements. Yeah?
Well, if we have it like you did on the previous slide, that the impulse is equal to the change of momentum in a cart generally, would it not be easier to just prove that the impulses were the same between them, and then that implicitly proves that the change in momentum is the same?
So the answer to that question is yes, absolutely. But the problem with that is that if these carts are rolling toward each other and collide with each other using the plunger, then we're only going to be able to use the force sensor for one of them. So how do you know that the impulse is the same? Because if you're right, then absolutely that would be true. But we can't measure the impulse on both carts at the same time if we collide them this way. Now, you might be able to collide them a different way, but this way seems to work. So that's a great point, which is that like there's a lot of mathematical stuff that could potentially go into this. If we wanted to just investigate the hypothesis that I proposed, though, what we would need to do is find the impulse on one of these cards, like the yellow card. To do that, we would need to know the average force acting on that yellow card and the amount of time over which that average force occurred. That would allow us to determine the impulse acting on that yellow card. And to find change in momentum, we need to know the mass of the green card, and we need to know its velocity before the collision, and we need to know its velocity after the collision. That would allow us to find its momentum before the collision and its momentum after the collision, which would allow us to determine its change in momentum. So that means that we need to make 4 measurements for each collision. We need to measure the amount of force on average acting on one of the cards, the amount of time over which that force occurs, and the velocities of the second card. Mass is easy. I mean, we need to make that measurement, but mass is easy, and potentially we could just make that once, right? So this card, for example, has a mass of 0.3. I could collect repeated data with that same mass, so well, I could change it, but I don't have to. So what I'd like you all to do for the rest of the period, and we're gonna pick this up again on Thursday, is to get to a point where you can routinely and accurately collect all 3 of these pieces of data from a collision between 2 cards and track them. And mass, like I said, is you'll need mass as well, but we've got balances and we don't even need them because we already know what the mass of the cards are. But in order to be able to collect meaningful data, we've got to be able to get these 4 chunks. So what I'm going to ask you to do is just practice that data collection now until you get to the point where you can just like effortlessly get that information. And then on Thursday, we're going to collect data, we'll analyze the data, put everything together in a cogent, coherent report that convinces me that you know everything that there is to know about momentum, impulse, change in momentum, and how to collect good data using supercards, etc. Right? So you have the rest of the period to get that worked out, and let me know if you have any questions.